Hi everyone, my name is Maddie and I'm here with my team IV Site. We are an interdepartmental team comprised of bio, mechanical, and systems engineers, and we're creating a device to detect peripheral IV infiltrations. So you may be wondering, what exactly is an infiltration? An infiltration occurs when an IV inserted into a patient's vein is somehow dislodged from the vein, causing the fluid from the infusion to build up in the surrounding tissue. When this happens, nurses must immediately, or as soon as they can, remove this IV to prevent any complications from occurring, and then a patient must be reinserted with a new infusion with a new IV. As someone who grew up experiencing IVs every other week of my life, I still remember sitting in the hospital chair as my mom looked on, called me a human pincushion every time my IV would infiltrate and the nurses would have to stick me again. And as we were going through this, we really wanted to keep this in mind and our patients in mind. My situation is not unique though. 100 million pediatric patients receive IVs every year. And after talking with nurses at the Children's Hospital of Philadelphia, right in our backyard, we learned that infiltrations occur in over 20% of these cases. Pediatric patients are inherently at a higher risk for infiltration due to their small, fragile veins and general lack of subcutaneous tissue. Additionally, these small pediatric patients may be unable to verbalize to their nurses that they're experiencing pain or any kind of symptoms associated with their IV. So I was very lucky that none of my infiltrations ever resulted in serious complications. However, some patients aren't so lucky. If we look, we can see that over 25% of infiltrations reach stage 4. This is generally a slower moving process that starts with bruising, swelling, scarring, and can lead to nerve damage. These stage 4 infiltrations are due to generally the lack of blood delivered to the blood vessels from the entire venous system. Overall, when we were looking at these, we wanted to make sure that we could design a product that would make sure that patients receiving IVs could be safe during the entirety of their infusion. And now I'm going to pass it off to Jill to talk about how these infiltrations are currently detected.
Thanks, Maddie. So when creating the design of our device, we wanted to see what methods were currently being done by nurses at hospitals to detect these IV infiltrations. So as Maddie mentioned earlier, we began by conducting observations at CHOP. Here we were able to interview nurses at different departments and see firsthand how the procedure is done. One important thing that we did learn was that currently there's no foolproof method to determine if an infiltration is occurring or not. Right now, the nurse will look around the IV site and they'll look for 2 key components to see if an infiltration has occurred. The first one is temperature. If the temperature gets colder around the IV site, that concludes that there is fluid that's built up and it's not actually in the vein, causing them to see that an infiltration might be occurring. The second one is skin swelling. So if the fluid has missed the vein, then the skin will expand and the nurse will be able to determine that physically. Also, we noted that these observations occur hourly. So we wanted to create a device that would take this data and then be displayed on a dashboard that the nurse could look at instead of just doing their hourly observations. They could have a dashboard device. So with that, we created IV Site. This is what's worn on my wrist, and it is a non-invasive monitor that will take in the biological inputs from the patients themselves alongside our own risk assessment algorithm in order to determine if a peripheral IV infiltration has occurred or not. When creating our device, we looked for 2 key components for this design. The first was nurse approval. We wanted a device that the nurses could easily integrate into their daily checkups, and we wanted their workflow to ultimately be declined. The second thing we looked for was patient comfort. We specifically targeted the pediatric departments, so we wanted something that could be worn by children and easily adjusted from patient to patient. That's why we went with our adjustable silicone band. I'll now hand it off to Emma to talk about the overall system design.
Thank you, Jill. So as Jill mentioned, we use 2 main key inputs. That is what a nurse currently detects. So that is temperature and swelling. To do so, we selected 2 sensors, a thermal camera sensor as well as a flux sensor. The thermal camera sensor provides an image of the vein where the IV is inserted and provides an 8x8 pixel image of what the temperature layout is of the vein. Next, the flux sensor is taped directly onto the skin, so it shows for any degree of swelling that may occur when there is fluid buildup. All these inputs go to a risk assessment algorithm, which alerts the nurses when there is a case of infiltration. So based on our testing, which we did on porcine livers, we found that about a 5-degree decrease in temperature, which is when the colder fluid is building up in the warmer tissue, kind of is the baseline for an alarm for when a nurse should check the IV, and then a 3% bend in the flux sensor after the flux sensor is calibrated to the patient. On the remote interface, the nurse is able to look at the granular data that the sensors are showing. So there's a 5-minute update for the temperature sensor, as well as a 2-minute update for the flux sensor, and then also the pixel-by-pixel image of the thermal camera, as well as a bend calculation to show the actual percent bend over the change in time over the course that the IV is given. So to take a closer look into the hardware, this is what IV site looks like. There's a flux sensor outside of the vein where it's placed directly onto the skin. Afterwards, there is a temperature sensor calibrated directly 1 centimeter above the skin, pointing down at the vein. And then we chose an Arduino Micro for size and a Bluetooth module to transmit the data to the nurse's station. And then overall, it is powered by a rechargeable 3.3 volt battery. IV site integrates into the nurse's workflow. Integrates into the nurse's workflow, where all the nurse has to do is strap the IV site onto the patient's wrist and then place a tape over the flux sensor directly above where the IV catheter has been inserted. And then from there, after those 2 easy steps, the nurse can go to the nurse's station and start monitoring the real-time data that's coming from their patient. So now I'll pass it off to Eric to talk a little bit more about the remote interface.
Thanks, Emma. So our IV site device will transmit data wirelessly to a web application that Emma mentioned, and this is what the nurses will be seeing. So we have on a home page a very simple to read, color-coded assessment of the risk of infiltration, categorized in low, high, and medium. And a big part of our device is for it to be an assistive tool to the nurses to help them reach their own conclusion of whether an infiltration has occurred. Nurses don't want to just trust a black box. So we have the ability for our interface to dig more granularly into the data for the nurses, to allow the nurses to view what exactly the sensors are reading. So in this case, we display the pixel-by-pixel image of the temperature readings and a time series of the skin swelling and the average temperature at the IV site. So IV site monitors swelling and temperature changes continuously, and specifically what we look for are sustained changes in these biological inputs. And the important part about this is that nurses don't have to continuously monitor the patient in that case. And also by looking for sustained changes, we increase the sensitivity and specificity of our detection algorithm. Additionally, our device will alarm the nurse's pager when in the case of an infiltration, and these alarms will be calibrated based on the degree of severity of the risk. And what this allows is that the nurses can avoid alarm fatigue in this sense. And lastly, as I mentioned, the key part of our device is to serve as a nurse's aid to help them assist in coming to a conclusion about whether an IV has occurred. And so we've designed our device to allow the nurses to use IV site more as a tool, not just blindly trust IV site to tell them when an infiltration has occurred. And the goal of these 3 components is so that we can enhance not only the user interface for the nurses with this device, but also the user experience. And now I'll pass on to Bridget to talk more about the cost of our device.
Thanks, Eric. IV site will allow hospitals to save on costly infiltrations. The typical infiltration costs a hospital around $2,000. This includes the material cost of the IV, the additional procedures required, as well as the labor from nurses and specialized teams. Our device, IV site, will cost just $200, and this will result in a 90% cost saving per infiltration for hospitals. Looking more closely at this cost breakdown, IV site will be able to achieve an 82% profit margin. Most of the costs incurred in the development of this device include overhead, including the salary of a support engineer, as well as the direct cost of the materials required to fabricate the device. Another cost associated with this device is the labor required to actually create the device. IV site development will be able to continue at CHOP. We are currently working with doctors at CHOP, including the director of anesthesiology and the chief of the NICU, who are all very interested in solving this problem of IV infiltrations. We'll be transferring our technologies to these doctors so they will be able to continue work on this development. And through their development, IV site will be able to be adopted into our target market of the NICU. IV site allows patients to, through our design of our device that allows patients to remain safe as well as save hospitals on these costly infiltrations, we hope that IV site will be able to make sure that patients in a situation like Maddie will be able to remain safe while receiving IVs. Thank you, and we'll take any questions.
Just a question of cost line.
Yeah.
So perhaps I'm not understanding this correctly, but it was $2,000 cost for infiltration, but the probability of infiltration is only 20%.
Right.
The expected cost per patient at $400?
Yeah, so we worked that into our margin. We did realize that it was around $400, but we just kind of, for the sake of pricing it, we worked the percent incidence of infiltration into our margin. So once it's actually produced on a wholesale level, it would adjust to the actual rate of incidence of an infiltration.
So how much training is required on average for a nurse to get proficient with technology and then
So the training process involved in a new technology kind of goes through a series of steps. First off is a pilot. So that's just a couple of days where the nurses, for like their 3-day shift per week, are utilizing the device in their hourly rotations. And then from that pilot, those nurses that are then trained can use it in their daily bedside routine. So usually around kind of 36 hours of training in their kind of 1 week span for their time range that they're in a hospital.
And still, the cost is still, you're not preventing the infiltrations, you're detecting them early. You said the $2,000 cost per infiltration, is that for post-care of an infiltration? Because you're not going to save the IV, and another IV has to insert anything.
Yeah.
So it's the post-care difference between detecting early and not detecting early?
Yeah, the $2,000 is incorporated with all the potential procedures that might be needed, including amputation procedures or any kind of surgical remedies. So that is an overall average of those prices.
And follow up with them, you said it was Bluetooth enabled, but Bluetooth doesn't have enough of a range to get to the nurse's station.
So it would be the nurse's station that's in the hospital room of the patient. So the one that's around 10 feet,
station.
like 10 feet from the bedside.
Were you able to test the device in any way and determine what the success rate might be? And if not, have you thought about what kind of testing would be necessary to validate?
Yeah, we can do that. You have the clicker? Yeah. We were able to test on pig livers, actually, which was recommended to us by a number of different surgeons who recommended that it would be the closest thing to an actually vascular system. So that being said, you can run the video or...
And then with the team we're working with in CHOP, which we're handing over to about next week, they have a lab prepared that's live sheep and pigs, where they would actually be able to insert, or we'd be able to test some IVs that are already inserted into animals to get an idea of an actual vascular system.
The damage to the patient is tied to the amount of time it takes to actually identify that there's a problem. So the thermal sensor is 5 minutes?
Yeah.
So do you have a plan to basically get that down to 2 minutes, which is similar to what you've got for the swung sensor?
Yeah, so the reason we chose different timing for the flex and the thermal is that thermal is kind of detected first. So we wanted to get a sustained change to make sure it wasn't the patient moving the device or extra like fluid or water spilling onto it. It's because the thermal of the actual body reacting is more slow than the actual swelling, which is based on the flow rate of the pump. Any other questions?
Thank you very much. Incidence in an adult versus a child?
Incidence in adults, I believe, was around 10 to 15%. So it's generally, I think the rate though is generally a much more extreme in terms of the stage 4 infiltrations is much higher in children. So it's relatively similar because this can happen in either way, but it's much easier to detect the smaller ones and the ones that aren't as extreme in adults.
All the time. Thank you.
Thank you.